So the notion of a derivative makes sense when we're talking about functions of one variable. We've worked with the derivative now for a while, so hopefully all of you guys are familiar with it, because if you aren't, you're in big trouble now. Because we're going to move on to sort of this notion of a partial derivative, which can only be really done when we talk about functions of several variables. So derivatives of functions in one variable were straightforward in the sense that we didn't have to worry about the direction of the derivative. When you took a derivative, there was only one direction, the x-axis, right? Just to the right, positive, negative, that's up, down. That's all we really cared about. So the slopes of all the tangent lines only had one possible orientation, positive up or negative down. However, when you consider functions of several variables, the domain, the space of inputs, is now a plane, at least in two variables. So in order to understand sort of how the graph changes in these directions, we have to consider the partial derivative. Because ultimately, what the derivative did is that it told us how the function would change over time, right? If your slope was positive, your function would increase as it moves to the right. If your derivative was negative, your function would go down, decrease over time. So it told us how the function would behave along the x-axis. We want to somehow get this information once again, but in this more general planar setting. So we're going to define the partial derivative of f with respect to x at the point AB as follows. So f sub x at AB is going to be the limit as h approaches 0 of f of a plus h comma b minus f of a comma b divided by h. Mouthful. Okay, so basically the key thing here is that the x component of your f function is the one that has the plus h, but the the y component of both functions here do not change whatsoever. In a similar fashion, the partial derivative of f with respect to y at the point AB is going to be this limit here, where the a's, the first components, do not change, but the second component has this h factor instead. Excuse me. And so these will be the partial derivatives, provided these limits exist. So visually, what exactly is happening here? So last time, or I shouldn't say last time, in functions of one variable, you would calculate the derivative by taking slopes of secant lines, and then you take the limit as these points would get closer and closer and closer together, and that will give you the slope of the tangent line. Okay? However, when we have a three-dimensional space, so let me actually make this a little better. So now that we have a three-dimensional space, the problem is that we can have really weird sort of kinds of surfaces like this, right? So let's take a point over here. So ultimately, what the partial derivative of x is doing, at least geometrically and visually, is that we are going to take f of a plus h. This is AB. Well, I guess really down here is AB. So this is AB. So f of a plus h comma b minus f of a comma b. This over here is f of AB. And then f of a plus h is going to be, so this is a plus h comma b. And this is along the x-axis, right? Because you're only adding a little bit to the x component of your function, right? It's a plus h, which is over here, along the x-axis. So then f of a plus h comma b is going to be over here. And so the difference in these 2 points is going to be this z difference over here. And what we're doing is we have this component over here, this h component over here, this distance of h along the x direction. Consequently, the distance between these 2 points is going to essentially be something like a secant line, and really we're only caring about the changes along the x direction. So a partial derivative with respect of f with respect to x is really like a derivative along the x-axis. And so we get a sense of how our function will change as we move positively or negatively along the x-axis here. So this is moving down a little, so we have a sort of curve going downwards in both directions and then back up. So it sort of looks like this. So it sort of looks like this. On the other side, we have, I'm going to draw something like this. So here, this is now going to be along the y-axis. So here, this is sort of how the function will change as we move in the y direction. And this sort of determines what the partial derivative of the partial derivative of f with respect to y will be. So yeah, so the partial derivatives with respect to x and y is essentially the usual derivative along these particular axes. In addition to the notation f sub x and f sub y, we also use the following notation to denote partial derivatives with respect to x and y. So this is the partial derivative with respect to x. The main thing to notice are the curly brackets. We don't use d by dx, we use partials instead. So that's basically the main difference from the normal derivative. Everything else is pretty standard. We have, our new notation of subs for partial derivatives here, and then the rest are fairly familiar, hopefully. So in the same way we can go from the definition of derivative to a number of differentiation rules, we can also simplify partial differentiation similarly. It's really important that we don't have to go through this limit definition every single time. That was the case back when we had functions of one variable. It's the same now that we have functions of multiple variables. We do not want to deal with the limit definition over and over and over. And so from these definitions that we have here, these two definitions, these limit definitions, we can, if we want to take the partial derivative with respect to x, we treat the y variable as a constant, right? Here, the b is the same for both of these functions. So if your function was something like x squared times y, for example, so let me write that again. So if you have the function f of x comma y is equal to x squared times y, then here, since your b is not changing in both of these sort of components, we can treat this y part as if it's a constant when we're taking the partial derivative with respect to x. And I'll give you an example to make that a little more clear after I finish sort of this precursor discussion. So if what you need to do is you treat the y variable as a constant, and then you differentiate the function f of x comma y normally with respect to x, so the usual derivative. And the same sort of concept holds true when you're differentiating with respect to y. You will hold the x component constant instead. So here, I'm going to take this derivative with respect to x. Take the partial of this derivative, of this function rather, with respect to x. So partial f partial x of x comma y is going to be, so y is a constant. So if it's a constant, then really it is a constant times x squared. So really, if you're differentiating something with respect to a constant, you can pull it out of the differentiation, right? So really, I have y times the derivative of x squared with respect to x. That is what this partial of f with respect to x turns out to be. It's y, which is now a constant with respect to this differentiation, times the derivative of x squared, which is just 2x. So the partial derivative of f with respect to x of x squared times y is 2xy. However, let me just make this a little neater over here. if I want to differentiate this thing here with respect to y, so I have partial of, oops, that is not what I meant to do, partial of f divided by, partial of, words, my bad. Partial of f, partial of y, x comma y. So I'm differentiating f with respect to y now. I treat y as a variable, and x squared is going to be my constant. So this is y times some constant, and I'm differentiating this with respect to y. Well, since it's just y, we use the power rule normally, so our answer becomes x squared times 1, or just x squared. So the two partial derivatives of the function x squared times y are 2xy for the x partial and x squared for the y partial.